Let us now turn to the internal motions inside elliptical galaxies. This turns out to be really the key to their nature and understanding. So the stars in elliptical galaxies have largely random motions, and so therefore their kinetic energy can be characterized by a velocity dispersion. You can think of the distribution as being pretty close to Gaussian. Because they're supported by random motions rather than rotation, they're called pressure-supported systems. And the way we usually measure this is through Doppler broadening of their absorption lines. As I'm sure you know, spectra of galaxies composed of stars have many different absorption lines due to different elements. And each of these lines is pretty sharp when it originates, but because there are many, many different stars moving at random velocities, the total observed line will be a weighted sum of those, and its shape will reflect the overall Doppler broadening by the velocity distribution. So by deconvolving an unsmeared line, say from template spectra of stars that are like those that make ellipticals, convolved with, say, Gaussian distribution of Doppler shifts, we can infer what is the underlying velocity dispersion of the elliptical galaxy. Note that whereas we measure rotation by simple shift of a line to red or blue, here the line is not shifted, it's just broadened. And here are some velocity profiles of elliptical galaxies. The velocity dispersion on top, rotational speed on the bottom. In some cases, there is actually a rotational component. Those tend to be disky ellipticals. In other cases, there is no net overall rotation, but there is a lot of velocity dispersion. Generally speaking, velocity dispersions tend to be higher near the center of the galaxy, but by and large, they remain nearly flat, by analogy with flat rotation curves of spiral galaxies. A nice new way to measure this is so-called integral field spectroscopy. Here, a spectrograph is composed of many different entrance apertures, usually that's done with optical fibers, and then spectrums taken of each one of those. So you're getting a spectroscopically resolved picture on the sky. And from that, you can reconstruct what Doppler shifts and broadenings are anywhere across the face of the galaxy. You can also add up all the light, and then you have surface brightness distribution. So here are some examples from a group with an instrument called Sauron of several elliptical galaxies, as indicated here. The top row shows their surface brightness distribution, just adding up the light. The middle row shows the rotational velocity component, and it's coded in intuitive fashion, red ones going away from us, blue ones approaching us. And you can see that there is definitely some rotation present in some cases. Actually, in all cases in this particular set, which is not chosen randomly. And the bottom shows the distribution of velocity dispersion. There you can see there is generally tendency to be a little higher in the middle, but otherwise it does not seem to have much of a shape distribution. So when velocity dispersions and rotational speeds were measured for ellipticals, to everybody's surprise back then, it was found out that shapes are not all due to the rotational velocity. And you can compute from simple dynamical models that for a given ellipsoid that's supported largely by rotation and has commensurate amount of random motions viewed from different angles, what should be the ratio between maximum rotational speed and velocity dispersion? And you can divide the two, and so for purely rotationally supported oblate ellipsoids, that's a line in the diagram that shows the ratio of velocity to the rotational speed to velocity dispersion as a function of ellipticity. As it turns out, ellipticals do go up to that line, but most of them are below, meaning that they have too little rotational speed for their ellipticity and their random velocity component. And so that also means that they cannot be supported entirely by rotation. There could be, that's sort of the upper envelope. There can be none of the rotation, that'll be the 0 point on this diagram, but they're somewhere in between. And so a great majority of elliptical galaxies are supported by velocity anisotropy. Now you can take that ratio of maximum rotational speed to velocity dispersion and the line for perfect oblate rotationally supported ellipsoid and normalized by that line, so that rotationally supported oblate ellipsoid will have the normalized value of exactly 1. And lower than 1 means more anisotropy. So now we can plot this normalized quantity, the relative importance of velocity anisotropy, as a function of, say, galaxy luminosity. And it was found that more luminous galaxies are more anisotropic. This can be understood as a consequence of random merging. You may remember that disks have to involve dissipative formation. You have to dissipate energy, not angular momentum, get a disk, then make stars. Whereas random merging does not preserve rotation, it scrambles up any rotation and just creates pressure-supported system. So if indeed you build up ellipticals through random merging, then you would expect the more luminous ones to be more anisotropic, and that's exactly what we see. As we measure spectra, we can tell about chemical composition of stars, not just their velocities. And so we can measure strengths of absorption lines of elements such as iron or magnesium, which are fairly common, and use that as an indicator of the chemical evolution history of the galaxy. So it was found that elliptical galaxies are more metal-rich near the middle than on the outskirts. That is, there was a more recycling of interstellar material through subsequent episodes of star formation in the central portions. Now, you cannot do this through merging. In fact, merging will scramble any such arrangement. So there has to be a dissipative self-enrichment component to the formation of ellipticals that then reflects itself through this dependence of stellar population as a function of redshift. Now, spectra are hard to obtain because they require long observation times. A much easier thing to measure are colors, which are ratios of fluxes into different filters. Now, it turns out that more metal-rich stellar populations have more absorption lines in the blue part of the spectrum, removing some blue light. So the more metal-rich populations will have a redder color. And you can measure colors fairly easily, use them as a proxy for the metallicity of galaxies. And it turns out that more luminous ones are redder. They're more metal-rich, and you may recall that there's a picture whereby supernova ejecta, which is where metals come from into the new generation of stars, can escape from low-mass galaxies, but are still bound to the higher mass host galaxies where it can be recycled into new stars. So it makes sense that subsequent episodes of star formation in deeper potential wells, in more luminous, more massive galaxies, would result, after a little while, in a more metal-rich stellar population. So we see that both within individual galaxies, more metal-rich stuff near the middle, and between different galaxies, the more luminous or more massive ones retaining more of their metals. Likewise, you can use velocity dispersion instead of luminosity and find out that those which have higher velocity dispersions, which are really kinetic energy per unit mass, therefore reflecting in virial equilibrium the depth of the potential well, also have higher metallicities. Deeper potential wells, more recycling of the metals. We already talked about gas in elliptical galaxies, where spiral galaxies have plenty of interstellar medium, cold one, hydrogen mostly. In elliptical galaxies, there is hardly any cold gas, only if it's been recently accreted, but there is plenty of gas all told. And that gas comes largely as a product of stellar evolution, but some of it's accreted from the outside. It's heated to millions of degrees, which is a virial equilibrium temperature for the corresponding potential wells in elliptical galaxies. Now that we can measure kinematics of ellipticals, reflecting their potential wells, we can fit dynamical models and find what their masses are. So here is from a large survey of elliptical galaxies by a group called SPIDER, Lar Barbera and De Cavallo and collaborators, plot of stellar masses come directly from integration of visible light versus dynamical masses, which are now inferred from kinematics, velocities of stars reflecting total mass, not just the visible component. And they're proportional, right? But there is a trend. The more massive galaxies tend to have a larger component of dark matter, or I should say, more mass is in form of the dark component. So most galaxies are in this band where one envelope is that there is no dark matter, there is just stars. The other envelope is that dynamical mass is about 6 times the amount of visible mass in stars. Interestingly enough, that corresponds to the ratio of omega matter to the omega of baryons in the universe at large. If you can think of stellar mass as proxy for luminosity, then that means that mass to light ratios will be higher for the more massive galaxies. And that's indeed what's seen through a number of other pieces of evidence. So fitting dynamical models in detail to galaxies, we can figure out exactly what their masses are, and you can plot mass to light ratio versus luminosity or versus mass, and here they are. The more massive or more luminous galaxies tend to have higher mass to light ratios, which a priori need not specify the amount of dark matter. It could be there is invisible baryons, but there are good reasons to believe that, in fact, most of this is due to the relative abundance, relative amounts of dark to luminous matter within the regions where we measure this. Now, notice that qualifier. We remember that we already talked how in galaxies, baryonic component is more condensate than dark matter. Dark matter halos are fluffier, dominate more at large radii. This is certainly true in elliptical galaxies as well. So if you're measuring velocity dispersions and whatnot in the luminous parts of the galaxies, you're liable to be finding mostly luminous baryonic mass. If the ratio of distribution of dark and luminous matter changes as a function of mass, so the halo distributions are more extended, but the light distributions tend to be more condensed for smaller galaxies, as is indeed the case, if you remember how surface brightness profiles depend on luminosity, well then you would expect to see just this. So it's not 100% clear at this point how much of this effect is due to different distribution of luminous and dark matter versus different amounts of luminous and dark matter. It's probably a combination of both. The gravitational lensing provides a completely different way of measuring masses, independent of all this kinematics. And so this was done for sample galaxies using galaxies themselves as lenses. And what's plotted here, confusingly in the same diagram, is the mass to light ratios for the total mass, that's sort of the tilted component, and for the luminous mass alone, which is kind of flat component. And we find out that for the luminous mass alone, mass to light ratio doesn't change as a function of mass, meaning ellipticals of all different masses have the same stellar populations, and consistent with what we expect from stellar evolution models. But there is always more total mass, so higher total mass to light ratio, and more so at higher mass end, which is exactly what you've seen from previous diagrams, but this time measured in a completely different way, thus giving us some confidence that this is in fact correct. Yet another independent way of assessing this is through their X-ray profiles. Just like we used X-ray measurements to constrain masses inside clusters of galaxies, you can do the same thing inside elliptical galaxies. And there again, you find out, using X-ray gaseous test particles, that the ratio of total or non-luminous mass to the luminous ones increases as a function of radius. Next time, we'll talk about supermassive black holes in galactic centers and something that's completely unrelated, dwarf galaxies.